Next, making buildings sturdier so they can withstand the force of an earthquake. Tomorrow marks a year since Haiti's devastating earthquake. As we continue our series of reports about Haiti, NewsHour science correspondent Miles O'Brien looks at what researchers are doing to lessen the fallout from another disaster.
When the ground shook beneath Port-au-Prince a year ago, structural engineer Kit Miyamoto dropped everything. And in 3 days, he and his team were in Haiti, trying to figure out what they could do to help.
It's like almost kind of like a war zone here, isn't it? It's like a World War II movie here.
The magnitude 7 earthquake destroyed 250,000 homes, leaving 1 million people homeless. 300,000 were injured, 230,000 killed. The World War II analogy persists.
Just put in perspective, nuclear blast in Hiroshima killed 200,000 people, right? And it took Japanese government 10, 20 years to really rebuild the Hiroshima.
From Japan originally, Miyamoto came to California as a teen and has been in the business of designing and retrofitting buildings to better withstand earthquakes for 20 years. We met at his most famous retrofit project, the flying saucer-like theme building in the middle of Los Angeles International Airport.
I mean, as an engineer, someone who has committed his life to making structures safe and earthquake hardy, if you will, when you see that, what goes through your mind?
I just thought incredible, because we knew there's a risk there. All the engineers knew that. And also all the engineers knew about how to repair those, fix, strengthen those buildings before the earthquake.
Purdue University seismologist Eric Calais also came to Haiti a few days after the quake to gather some data. His efforts are featured in the new PBS NOVA program, Deadliest Earthquakes.
So this whole area here has moved 30 centimeters to the east during that earthquake.
Since 2003, Calais and his team have measured the movement of the fault that fractured beneath Port-au-Prince. As he watched the slow-motion collision of the Caribbean and North American tectonic plates, he knew a big quake was inevitable.
The last earthquake on that fault occurred about 250 years ago, and it's building up elastic energy at 7 millimeters per year. 7 times 250 is about 1.8 meters.
1.8 meters, or 6 feet, of stored strain equates to the energy of about 100 Hiroshima bombs. In 2008, Calais foresaw a magnitude 7 earthquake.
What we saw was a fault being loaded, just like a rubber band.
He knew it would snap, but he could not say when.
We cannot predict earthquakes. We had no way of telling whether it was going to be today, tomorrow, in 10 years, in 100 years, so we didn't put a date on it. And it's not that we were afraid to put a date on it. As a scientist, we can't.
So saving lives is more about keeping buildings intact than early warning. Structural engineers have learned a lot about this over the years by shaking buildings to see how they might fail. I got a first-hand taste of the technique on the roof of the Millikan Library at the California Institute of Technology. Flip the switch, let the heavy disc spin, and the building starts swaying.
Holy cow. Wow. It's an artificial earthquake. Yeah. And it's all for the good of science and good engineering. For real. So, could you shake this building even more than this? Is that possible? Or?
I guess like for full weight,
yeah,
the maximum is this amount.
This is it, but you really get a sense of the swing.
Engineering seismology professor Tom Heaton presides over the shaking, not to torment the studying students below, but to understand the building's frequency.
So this type of motion tells us how the building dances around an earthquake. So for a tall building tends to vibrate at some natural frequency, almost as if you were looking at a slow motion picture of some sort of tuning fork that's vibrating at some pitch. And so if you excite the building at the natural pitch of the building, the vibration just gets bigger and bigger.
This is what happened in Mexico City during the devastating magnitude 8 earthquake of 1985. The ground did not move violently, but the tremor lasted a minute and a half, and its frequency was just right to make the tall building sway more and more until they toppled.
All the highly engineered, very well constructed buildings were the tall buildings, which were the ones that actually collapsed. And the reason was because the ground motion was tuned to the tall buildings.
So earthquake engineers spend a lot of time thinking of clever ways to reduce the swaying.
It's also a hardship.
Back at the LAX theme building, Kit Miyamoto and I slithered our way inside the $10 million system he designed to help the 50-year-old icon ride out a magnitude 7 earthquake.
Well, obviously, I'm not in the observation deck here. Below me is the building. Above me is 1.2 million pounds of steel, equivalent to the weight of two 747s. Attaching the two, 8 of these giant dampers, shock absorbers, if you will. Here's how it's supposed to work. If there's an earthquake, the building moves this way, the steel above goes that way. It's a giant counterweight.
Having that, it reduced the motion of the structure to 4 inch to about 2 inch.
But the engineering and the systems that allow buildings to withstand tremors do not have to be as elaborate as this.
This is the Church of the Angels in Pasadena, California. Church was built in 1889 as a memorial.
I met veteran U.S. Geological Survey seismologist Lucy Jones at her church in Pasadena. In 1889, a rock and mortar wall supporting a roof probably seemed like a good idea. But it is the worst possible construction technique in an earthquake zone. In fact, it was outlawed here for new construction in 1933.
What an earthquake is shaking. It's forces just like gravity, but now they're pushing sideways instead of up and down.
So sideways gravity we don't build for typically.
We don't typically build for sideways gravity, but that's exactly what you need to do for an earthquake.
The church lost its bell tower during the big quake in 1971. And more recently, Lucy Jones made sure her fellow parishioners knew how vulnerable it was to even more damage. So they fixed it. The basic idea, make sure the roof would not have to rely on the masonry walls to stay standing.
The way this was done is that steel beams were put down through the stone walls, and then the roof was tied to those steel beams. And then inside we also have structural members to hold the roof together. And so that even if all of the mortar dissolves and the rock starts coming down, that roof should still stay up.
But retrofitting a well-endowed church or a well-known landmark may seem like a luxury Haitians cannot afford. Or is it?
You know, people see this elaborate system that you've built here, $10 million, and they think, well, it's too expensive to build a building that will ride out a 7.0 earthquake. And certainly a place like Port-au-Prince, Haiti, they can't afford to do it. Is that true or false?
It's a false. For example, right now there are over 100,000 buildings being damaged, and we're spending about average $1,000 per house to not only repairing it, but also the providing seismic strength at the same time.
Engineers say it is more about mindset than money. 3 months after Port-au-Prince was devastated, a quake of the same magnitude struck a city of similar size and means, Mexicali, Mexico. But only a handful died. Here, they're more attuned to the threat of earthquakes and distribute simple instructions on how to build with that in mind, like using rebar and metal straps, which were not commonly used in Haiti.
So far, our experience is good. That you guys are good engineers. I noticed that.
Kit Miyamoto is trying to spur Haitian engineers and builders to think differently.
We start, applying new techniques, okay? Just to, reinforce the wall and build them in the best way that they were not before.
Still, 1 year later, there are few obvious signs of rebuilding of any kind. But Kit Miyamoto remains optimistic.
Seems like nothing going on for a whole 12 months. Because it just seems such a chaos and such a mess, you know. But as you can see, that there is we understand what happened, and we understand how to fix it, and we understand how Haitian people can repair and engineer and fix those things together.
Block by reinforced block, it appears they are building better here, haunted by a natural disaster that was so much worse than it had to be.